So I do want to do a precursor for today, obviously not included in my time. As I've talked with Esty, with me, secondary chemistry, as you know, it'd be kind of hard to do a lesson in just 10 minutes. And so what I'm going to do today is based on the premise that this is actually kind of a spanned out, maybe even 2-day lesson in which I talk about forces within an atom. And there are 4 different types of forces. And so I would cover probably 2 the day before, and then today's lesson I would cover 2 of those. But with only having about 10 minutes, I'm only going to actually lecture on 1. And so I wanted you to know that some of the stuff will be off from the day before, and then what you'll see in the video is kind of a review of the day before, because it is important and also would act as my pre-assessment. And then you would see another little skip in which I would talk about electromagnetism, and I would get right into the strong force within an atom. And so I'll kind of put a little black screen explaining, okay, this is where I would cover electromagnetism. You know, kind of like a SpongeBob, 5 minutes later, kind of thing. So anyhow, I just wanted you to know, it'd be kind of, you're getting a 10-minute snapshot of what possibly is a 2-day lesson. And we'll kind of go from there. So we'll give this a go. Again, sorry, little side note. Obviously, as a teacher, normally I would have a podium or something that I might keep my notes on. Since this is 10 minutes, I am going to do a little bit of note looking at, and I'm going to just have to carry those in my hands. So again, I apologize if it makes noise. I'm sure you guys understand. So here we go. This is how I would start off. I would welcome everyone to class today. We're going to start off from where we were at yesterday, and talking about the intermolecular or interatomic forces, electrical and nuclear forces that hold atoms together. So as a quick review, and you know, it's been 24 hours, and I know people forget in 24-hour span. Let's go ahead and talk a little bit about where we were at. So who can give me an explanation of force? Tim, go ahead. What is an explanation of force? Great, absolutely. So we know that a force is any influence, either pushing or pulling, that gives energy to an object, which oftentimes changes the motion of that object, correct? Remember, we talked about soccer. If you kick a soccer ball, the force from your foot goes into the ball, changes the direction or motion of that ball. We're exerting force. We talked about how we exert force every day in our lives. We also talked about forces that occur when objects touch each other, i.e. foot to the ball. However, do forces between 2 objects that do not touch have an effect on one another? What do you guys think? Go ahead, Alicia. Well, absolutely they do. Do you have an example by chance? Okay, good example, right? Gravity. Now, gravity affects without touching. Look at planets, orbits, right? I don't know how many of you have taken Mr. Smith's astronomy class, but we know that gravity affects planets, right? It pulls planets together even though they're not touching them, right? Gravity holds the moon in place. So we know gravity affects things that aren't touching. So today we're going to talk quickly about electromagnetic forces and my favorite, the strong forces. So let's get going. So now we've talked about electromagnetism. Okay, now I want to talk about strong force. To understand strong force, let's start with the question, how do we know strong force exists? And to understand how strong force exists, we have to know a little bit about a chemist named Ernest Rutherford. In 1911, Ernest Rutherford came up with the basic structure of an atom. And when I say basic, due to the tools he had, he knew that there was a center that was positively charged, and he knew that there was a cloud of negatively charged electrons. And that was pretty much it. And it wasn't until 6 years later that Ernest, in 1917, that Ernest realized that that center, that nucleus, is not just a big blob of positively charged, but he was able to see that there were positively charged protons and neutrons put together that had an overall positive charge. And this raised the question, if I have two protons, this is a simple structure, but you have two protons that are positively charged, and we understand electromagnetism, we know that these should repel each other, like this, right? But they don't. We see that they don't because there's nucleuses all over. That's the structure of an atom. So obviously there's a force that pushes in on this. So let's discuss a little bit about these forces. We know from testing experience, and this is really cool, that this reaction, this electromagnetic force between the two positively charged protons is about 20 pounds of pressure, which may not seem like a whole lot to you and I in the world that we live in. But when you think about what 20 pounds would do to something subatomic like these protons, you have to realize that if they were allowed to separate, right, there was no forces enacting to push them together, that they would accelerate away from each other at about 8,000 miles per second. So this 20 pounds of force enacted on something so small accelerates these two things at 8,000 miles per second. We know that they don't separate, so we know that the force coming into them has to be at least equal to that 20 pounds, right? Now there's something else that we know. We know that if it was like for like, that we could easily kind of chip these protons off. We could knock them away. And we know that's not the case. We've observed that in order to get decay like that, to be able to chip off protons, sometimes takes millions and or billions of years. So obviously the force that's pushing them back together must really exceed 20 pounds. And through tests, through observation, we found that the strong force, the force that pushes these back together, is about 100 times stronger than the electromagnetic forces that are holding these together. Okay? It's much, much, much stronger. Now, oh yes, David, what's your question? That's actually a really good question. So class, what David asks is if this is so much stronger, this 100 times, and it's just pushing protons together, how come eventually not all protons, and I'm going to take it a bit further, David, why don't all protons eventually, everything in the known universe, why doesn't it become like this, just massive nucleus? That's a good question. And that comes from what's known as contact force, David. Let me explain contact force, and we're actually going to use the magnets to kind of help demonstrate this. So I'm glad you asked. We can look at the periodic table and see that any nucleus that has 100 protons or more becomes unstable. This is kind of where we get this 100 times stronger. Okay? The stable elements are anything 100 or less. So we know that about 100 times stronger affects only about 100 protons. So why does it only affect 100 or fewer and not more, right? Because then you're right, David, we'd have this 100 proton mass collide with this 100 proton mass and this 100 and eventually it would just be one big nucleus floating in the dark space. So obviously it doesn't happen. So let me demonstrate this using the magnets that we had, okay, for your electromagnetic portion. We know that there's a force enacted when we get these close together, right? They don't have to be touching. Just get them close together and they either push or repel, okay? That's the electromagnetic force right here that's repelling. Contact force is much like Velcro. And what I mean by that is we know that Velcro has a force, right? If I stick it together, it's hard to pull apart. However, if I stick it just close to each other, it doesn't pull them together, it doesn't push them apart. It has to be in contact, one with another, for that force to be enacted. And this is a much stronger force, but it has a much shorter range. We talked about electromagnetism. You could separate these two on the two sides of the universe, and they'd still, although unmeasurable by us, they still have a force on each other. But contact has to be relatively close and in contact. So to kind of demonstrate that, again, I have my large magnets. We know that there's a force right about here, right? There's about an inch, and it's pushing away from each other, and it wants to repel them. However, you'll notice I put Velcro in there, which demonstrates our contact force. And if I put them together like this, nice and tight, and I let go, you'll see that the Velcro, i.e. the strong force, has overcome the electromagnetic. In fact, if I pass this around or hold this close enough, you'll see that there's still a gap between these two magnets because they're being repelled. But the force of that Velcro, the strong force, is stronger than that repelling force. So here's an exact demonstration of how electromagnetic force, the repelling force, is overcome by a much stronger force, the strong force in Velcro. And one, the force enacts itself without touching, and the other, the contact force, has to be put together to create. So along those lines, once you get so far, let's say we had 100 of these, just stacked and stacked and stacked, and although they might interact on whatever's touching them, the force between a magnet, 100 of them up here and 100 of them down here, separated by so much space, becomes irrelevant. And so the force at some point becomes, in essence, overcomable by other forces. So strong force, David, I know it's a long answer. Strong force has to be close and connected. It's a contact force. So eventually it becomes so large that they're not in contact with each other, and other forces can enact their will, and thus we have space and things are not just slamming into each other, nucleus after nucleus after nucleus. This is my favorite force, the strong force. Believe it or not, and this is what we're going to end with, the strong force in an atom is the strongest force measured in the universe. We're talking rocket engines, black holes. The strongest force in the universe is this, the stronger force.